from the University of Edinburgh, and he will talk about strong lower bounds for constant depth Frege Imply lower bounds for Frege.
Thanks, Pavel, and thanks to the organizers for inviting me. I'm going to be talking about this connection between the proof systems Frege and constant depth Frege. So I know this is a workshop on logical approaches to barriers and complexity, but this is more of a complexity approach to barrier and logic. It's pretty much the same thing, I think, though. So this is joint work with Yuval Filmus and Tony Petassi at the University of Toronto. And feel free to interrupt me at any point. I don't think this talk will go over time. So this is the general plan of the talk. For the first few minutes, I'll just be introducing the problem and giving some motivation for considering these proof systems. And then I'll just be doing some definitional work, defining what Frege and constant depth Frege are more formally. And then we'll go to the proof of the main result. So the result is motivated by a certain complexity result, which is simpler to show. So I'll first be sketching a proof of this complexity simulation. And then I'll describe what's involved in carrying this simulation over to the proof theoretic setting. And then finally, I'll have a couple of corollaries of our main result and a few open questions. So this talk in the area of propositional proof complexity, and you might have seen other talks in this area in this workshop, but let me just go over the preliminary work again. So what is a propositional proof system as defined by Cook and Reckhow? It's any polynomial time computable onto mapping from the set of strings onto the set of tautologies. So this is like really abstracting out the notion of a proof and saying that the only important ingredient of a proof is that it's polynomial time checkable. So you need to be able to prove every tautology, and given a proof, you need to be able to figure out what the tautology it's proving is. So that's what F gives you. F gives you, given the proof, the tautology that is proved by the proof. And this is something that's polynomial time computable. And we say that Y is a proof of phi in the system F if F of Y equals phi. So the question in general is, for specific proof systems F of interest, are there sequences of tautologies which require large size proofs? And here large is defined either in terms of the number of variables of the tautology or in terms of the size of the tautology. And large usually means superpolynomial or sometimes exponential. And in fact, this distinction will be very important to us. So there are several motivations for proof complexity. I mean, one of the most natural motivations is automatic theorem proving. So clearly, automatic theorem prover has implicit in it some proof system, and then the question is which theorems are easy to prove in that proof system and which aren't. But there are also motivations from complexity theory more broadly and from algorithmic analysis. So in terms of complexity theory, we have that NP equals co-NP if and only if there's a propositional proof system in which every tautology has polynomial size proofs. So this was proved already by Cook and Reckhow in their original paper. And you can think of proving low bounds for most restricted proof systems as somehow making progress on the NP versus co-NP question. Well, I mean, this is something that I myself don't completely subscribe to because, well, it's just that there's so much of a, well, there's so little that's been done so far and there's so far to go that it's not clear whether there's a plausible approach. But the next motivation is one which I certainly do subscribe to, which I think is really interesting, and that's thinking of proof complexity in terms of algorithmic analysis. So often in the theory of algorithms, we're interested more in algorithm design. So we want to know, given a problem, what's the best algorithm to solve it. But I think it's also interesting, given natural algorithms, to try to describe what the best performance of these algorithms is. So do they perform well in general, or are there worst case examples that you can find easily? And I think proof complexity is a nice setting in which to study this question because natural proof systems can be thought of as classes of algorithms for satisfiability. So a proof system is naturally co-non-termistic, well, it's a deterministic, non-termistic algorithm for tautology, which is the same as a co-non-termistic algorithm for satisfiability. And if you somehow determinize the algorithm, I mean, you can determinize an algorithm in various ways. If you determinize the proof, then that gives you an algorithm for satisfiability. And so somehow proof systems give some kind of like a syntactic description of algorithms. And many interesting natural algorithms fit into this framework. So hard to prove tautologies now correspond to hard instances for these algorithms. So I'm going to be dealing mainly with these Hilbert-style proof systems, and many natural proof systems are Hilbert-style. So when I use natural here, I mean it in the common English language meaning of the phrase. So some of you may be aware of the work of Rasbrov and Rudich, who hijacked the word natural for their purposes. And I think that's a very unnatural thing to do. I mean, natural is a word that should be a cliche. I mean, anyone should be able to use it as they please. And so when I use it in the Rasbrov-Rudich sense, it'll be within scare quotes. And when I use it in this sense, it'll just be whatever I want it to mean. So natural proof systems are Hilbert style. So you're not going to consider just any arbitrary polynomial time computable function f. You're going to consider ones that correspond to proof systems that arise in the real world. So you have lines which are, each of which is either an axiom or it's obtained from previous lines by using a rule of inference. And the size of the proof is just the sum of the lengths of all the lines in the proof. And as some examples, so there's a resolution proof system, which is perhaps the most important, and the lines of that proof are just clauses. Then there's constant depth Frege, which is one of the two main proof systems we consider in this work, and that's there the lines of the proof are constant depth circuits. And Frege, the lines are formulae. And for these proof systems, generally the main rule of, so there are other rules too, but the main rule of inference is the cut rule, which allows you to derive A or B from A or C, A or not C, and C or B, where C is any formula, called the cut formula. So what is known in general about proof complexity low bounds? Well, I mean, I'm going to say very little about this, so just enough for my purposes. So there are proof size low bounds known for various systems, but the systems that I mentioned, the first major result was by Harkin, who gave a low bound of 2 to the square root n for PHP. So here I'm measuring in terms of the number of variables in the tautology. So if you describing the pigeonhole principle in a natural way with n squared variables, then you get a 2 to the omega n low bound. So that translates to a 2 to the omega square root n in terms of the number of variables. And then if you want something that's stronger, that's actually exponential, that's 2 to the omega n, then this holds for random KCNFs, and this is shown by Huatal and Semeredi. And there's a lot of other work with various alternative proofs, which I won't be talking about. And for constant depth Frege, well, there's something known as well. So the first results were due to Aitai, and then, well, I think stronger low bounds were obtained by Beaming, Pagliazzo, Krajicek, Pudlak, Pitasi, and Woods. And they got low bounds of the form 2 to the n to the 5 to the minus k for depth k Frege. So if you have constant depth Frege where the lines of the proof are all of depth k, then you have low bound of 2 to the n to the 5 to the minus k. And what's interesting here is that for a pigeonhole principle or for random KCNFs, it's almost, well, and especially for the random KCNFs, it's purely exponential, the low bound. While for constant depth Frege, the low bound degrades as a function of the depth of the proof. And the question now is, well, is there some reason for this? I mean, is there a reason why we can't get stronger low bounds for depth k Frege? And as far as Frege is concerned, well, we don't have any non-trivial low bounds at all. We don't have any superlinear low bounds. So that's a major open question in proof complexity. And what we're going to show is that these two questions are connected. So improving the low bounds for constant depth Frege, quadratic. Okay, so that's still non-trivial, I guess. Yeah. So, okay, that's not trivial. Okay, so quadratic is the best low bounds we have. But we are still very far, I think, from obtaining super polynomial low bounds. So our main result is going to be a connection between strong proof low bounds for constant depth Frege and proof low bounds for Frege. But, well, I mean, it's maybe it's more assured to state in the contrapositive. So we show that in general, if phi is any CNF tautology with proofs of size s, and if you have any k, any natural number k, then phi is going to have proofs of size s times essentially 2 to the s to the 1 over k in depth k plus 2 Frege. So if by making k larger and larger, you can get sub-exponential size proofs. So of course the exponent depends on k. But by making k large enough, you can get proofs of size 2 to the s to the epsilon for any epsilon. And if the original tautology has proofs of polynomial size, then well, then the tautology also has proofs of sub-exponential size in constant depth Frege. Well, and you can interpret this result in various ways. I mean, so if you're an optimist, you'll interpret it positively, and you'll say that if we have short Frege proofs, then we get constant depth Frege proofs that aren't too long. So that's one way, a wildly optimistic way of interpreting it. A slightly more pessimistic way, but well, I mean, there's still a tinge of optimism, is that maybe there's a new route to proving Frege low bounds. So all we need to do is to prove purely exponential low bounds for constant depth Frege, and then we'll have super polynomial size Frege low bounds. But the truly pessimistic way of interpreting it is that it's a barrier to showing strong constant depth Frege low bounds, because we believe that proving super polynomial Frege size low bounds is going to be hard to do. So that says something about the hardness of showing even stronger low bounds for constant depth Frege. So that's a really pessimistic interpretation, and that's the one I subscribe to, being a complexity theorist. So just to elaborate on this point, I mean, so despite years of effort, there aren't any, well, so I'm going to take back non-trivial again, but there aren't any super polynomial size low bounds for systems such as Frege and EF, extended Frege. And unlike in the case of complexity low bounds, well, I don't think there's a good understanding of why this is the case. As I mentioned later, for complexity low bounds, we do have at least some rationalizations of why they're hard to obtain, but for proof complexity low bounds, we don't have this. And our result shows somehow that, well, I mean, we don't get an explanation of why either of these proof complexity low bounds is hard to obtain, but we can at least connect them up. So at least these two barriers of getting stronger low bounds for constant depth Frege and super polynomial low bounds for Frege are related. So that we can at least say that much. So I should say something more about this, about the links between proof complexity and computational complexity, because our proof idea, well, certainly relies on such a connection. So there's a natural correspondence between these Hilbert-style proof systems and circuit classes, just based on the form of lines in the proof. So a resolution, well, so you have clauses, the lines are clauses. So resolutions somehow correspond to CNFs. And constant depth Frege corresponds to the class AC0, which is a class of functions computable by constant depth circuits of polynomial size. And Frege corresponds to polynomial size formulae, or equivalently to logarithmic depth circuits. And extended Frege to circuits, to Boolean circuits in general. So there's some kind of natural correspondence based on what the lines of the proof are. And somehow as the lines of proof get more and more complex, proving low bounds gets more complex too, just in the complexity theoretic setting. Well, and there's been some transfer of ideas back and forth between the two areas. So for example, monotone circuit low bounds have been applied to prove low bounds for resolution. So complexity theoretic techniques have been used to prove low bounds for resolution. And in the sense, for constant depth Frege, again, the low bound technique that's used is inspired by complexity theory. So it's a random restriction method, which was originally used to show low bounds for constant depth circuits. That's, well, crucial in obtaining the best constant depth Frege low bounds. And there's also this idea of feasible interpolation, which is a way of getting, in general, conditional low bounds for certain proof systems based on complexity theoretic hypothesis. And in some situations, you can also get unconditional low bounds. So there's certainly a lot of crossover of ideas, but in some sense, there's no like legal grounding for this. So in general, there are no formal implications known in either direction. So it's not known that computational complexity low bounds for a circuit class imply proof complexity low bounds where the lines of the proof come from that class, or the other way around, that proof complexity low bounds imply computational complexity low bounds. I mean, if you look at it in practice, well, the state of proof complexity seems to be slightly behind the state of computational complexity, but I don't see any intrinsic reason for this. I mean, it's just that technically, maybe complexity theoretic techniques have been used in proof complexity, but yeah, there's no reason why that has to be the case. And the thing is that computational complexity rationalizes its failure as well. So it has lots of explanations, relativization and natural proofs and algebraization and so on, for why it's hard to obtain circuit complexity low bounds. And for proof complexity, well, not yet. So we don't really have such rationalizations or explanations, as we charitably say. So our result, what it does is it tries to strengthen these connections between proof complexity and computational complexity more. So, so that's one of the contributions of this work. Okay, so I'm just going to have a few slides about formalizing the proof systems we're going to talk about. So there are various equivalent formulations of Frege and constant depth Frege, but we are going to be using the sequent calculus, where each line is going to be a sequent of the form that some sequence of formulas A1 to AK yields a sequence of formulas B1 to Bm. And the intended interpretation here is that the conjunction of the A's implies the disjunction of the B's. So a pk proof, a proof in the sequent calculus is just a sequence of these sequence, where each sequent is either an axiom, which is just an instance of A yielding A, or it follows from previous sequence by inference rules. So I'm going to describe the inference rules shortly. And the final sequent you want is just the null formula yielding phi. So that gives you a proof of phi.
Is PK stand for?
I'm not sure. Jan or Pavel? Oh, it's with a K. So, well, there are some kind of syntactic rules, syntactic sugar, so the structural rules, which is just saying some ways you can manipulate the order, or you can add some formulas to either side. So there's weakening, which says that formulas can be added to the left or right. So certainly, if you have a conjunction giving a disjunction, then adding something to the left is okay, and similarly with the right. And if you have two copies of the same formula, you can replace it by one, and you can also change the order of formulas on either side. So we won't be really discussing these rules again. I mean, they're just rules to make things more formal, the structural ones. The more interesting rules are the logical rules and the cut rule. So the logical rule allows you to introduce connectives into your sequence. So let me just discuss maybe the AND left rule. So if you have A, B, and gamma yielding delta, then well, that means that A and B and gamma yield delta. I mean, recall that the interpretation is that the conjunction of formulas on the left yields a disjunction of formulas on the right. So you just want to be able to add connectives to the left or right side consistent with this interpretation. And that gives you 6 logical rules for adding negation and an OR to the left or the right of the sequent. And well, and then there's the cut rule, which says that if you have A and gamma yielding delta and gamma yielding A and delta, then you can derive that that gamma yields delta. And the formula A is called the cut formula. And somehow the complexity of the cut formula is what distinguishes between Frege and constant depth Frege. So so both of these systems can be thought of as pk, but in Frege there's no restriction on the cut formula, so it can be arbitrary. While in constant depth Frege, we insist that the cut formula is of bounded depth. So we'll need to distinguish between two different notions of depth here. Well, the natural notion of a depth of a formula is just a number of alternations between ands and ors. So you look at the formula as a tree, and if you look at any root to leaf path, you look at the maximum number of alternations between and or, and you add 1 to that, and that's going to be the depth of the formula. But we'd also like, for phrasing our results, we'd like this notion of logical depth, which is just the depth of the formula considered as a binary tree. So that's just a syntactic notion where you have a tree and you look in the depth of the tree. So as an example, so if you just have an OR of 4 variables, then depending on how you parenthesize, the logical depth can change, but the depth is going to be the same.
Names are almost.
Yeah. Well, I mean, the word natural is used unnaturally, so I thought it used the word logically. But
Okay. From now on, we should put quotes to your
yeah. Yeah, we had some discussion about this actually. Apparently, this term logical depth has been used in this. I mean, yeah, I thought so too, but I was overruled. I don't know. So formalizing constant depth Frege, again, we are going to insist that all the cut formulas have depth that's bounded, that's at most k. And AC0K Frege, so the name reflects the connection with complexity theory with the AC0 circuit class, is just a pk where all proofs have cut depth at most k. And so note that the depth of the lines is not restricted. So earlier when we talked about constant depth Frege, we said the depth of lines was going to be restricted to be constant depth. But in this formulation, it's not. Only the depth of the cut formulas is restricted. And this allows us to talk about proofs of tautologies which are of large depth. So I mean, if you insisted that all lines had bounded depth, then you couldn't even talk about the proof of something which had large depth, but now we can. And when you're talking about proofs of CNF tautologies, then it's equivalent. Talk about lines having bounded depth or talking about the depth of the cut formula.
AC0 allow unbounded fanning.
Yeah, that's right. Unbounded fan ands and ors.
Talked there about binary trees.
So formulas, when we talk about formulas, we'll be talking about formulas as binary trees, but AC0 will be where you have unbounded Fanon.
So when you say AC0 Frege, I don't quite understand. Are you allowing them syntactically unbounded fine or not?
So that's the reason why I made this distinction between depth and logical depth. So AC0 is where the depth is bounded by k.
I see.
So you can think of it as a binary tree, but the number of alternations of ands and ors on any path is going to be at most k. So I'm going to state the main result in a somewhat more involved way. I mean, a couple of subtleties were lost in the original formulation. So, let phi be any formula that's provable in Frege in size S, using a proof with maximum logical depth d, where any line has maximum logical depth d. So it's essentially that the size of any line is 2 to the d. I mean, you can think of it that way. Then for every k, there's a k plus 2 depth Frege proof of phi of size. That's this S times 2 to the k times 2 to the d over k. So this simplifies to the formulation we had earlier in the case of CNF tautologies, but this gives a little bit more information because it tells you also what happens when phi is not a CNF tautology, when it has a larger depth, and it also gives you something more. So suppose you have a sub-exponential size Frege proof where the proof lines are all polynomial sized, then you still get a simulation with sub-exponential size constant depth Frege. So that's something that was again lost in the original formulation. So what really matters is the size of each proof line, not so much the sum of the lengths of the lines, and that's what the simulation corresponds to. An additional property that's true is that if the original proof is tree-like, then so is the new one. And this is going to be important in terms of getting a tight result in one of our contexts later.
So where do you see the lines here in this? You said the only thing is the length of a line counts.
Yeah, so it's kind of implicit. So when I say provable in Frege in size S, and I say maximum logical depth d, so the size of a line is somehow 2 to the d. So I'm distinguishing between the size of individual lines and the total size of the proof, which is the number of lines. And somehow the exponent only depends on the size of any given line rather than on the total length of lines. So if each line is polynomial sized, then you still get a sub-exponential size simulation, even if the number of lines is sub-exponential. So the idea of the proof, well, so it's carrying over, it's trying to carry over a complexity theoretic result to proof complexity. And the complexity theoretic result is that any function computable by a polynomial size formula can also be computed by a sub-exponential size constant depth circuit. And the general idea of the proof is to simulate each line of the Frege proof by a sub-exponential size constant depth circuit using the complexity theoretic result. But this is not enough because you need to be able to argue that these things are equivalent within constant depth Frege. And so that's what that's what makes the proof more complicated. So what I'm going to do is I'm going to describe first the complexity theoretic result and the proof idea there, and then how we refine it and modify it to get the proof complexity result. So the complexity result itself has quite a simple proof. So hopefully I'll be able to communicate it fully, and most of the content of the proof complexity one as well. So let's look at the computational complexity simulation first. So what am I saying? So let f be any function on n variables, which is computed by formulas of size poly in n. Then for any k, f is computed by k plus 1 depth circuits of size 2 to the n to the order 1 over k, where the constant of the order is pretty small, I think. So in particular, for any epsilon, f is computed by constant depth circuits of size 2 to the n to the epsilon. These are Boolean functions, yeah. And the simulation is going to use a divide and conquer approach, which is quite natural. So if some of you have seen the proof that parity is in sub-exponential size constant depth, then it's very similar to that. It's just kind of generalizing that. And we'll describe how. So well, first of all, you can assume the formula is balanced. So there's a classical result of Spira, which says that any polynomial size formula can be balanced to obtain an equivalent formula of size of depth c log n, where c is some constant. Well, a trivial case of that is where you have, well, if you have just one kind of connective, then it's trivially the case that you can arrange it in a balanced binary tree. But, well, maybe what's interesting is that you can do it even if you have arbitrary and or connectives. And so I'm kind of disguising what happens in the proof here because it's trivial for just ands and ors. But essentially, you can rebalance the tree and kind of guess information about intermediate nodes and then verify that information and thereby parallelize the computation of the formula. So this is something that we'll essentially take for granted. So we'll start off with the order log n depth formula. And then we have this notion of flattening a formula. So the formula starts off with depths at c log n for some constant c, and we're going to break up the formula now into layers, and then we're going to replace each layer trivially by a small depth formula. So how do we break up the formula into layers? It's quite natural. So we just, we're going to have k layers. Each layer is going to have c log n over k levels. So think of the first c log n levels of the formula, and then the next c log n over k, and so on. And each one of these is going to be a layer, so there are k layers. And now we're going to look at each individual layer. So individual layer, well, it has possibly many nodes in it, but let's consider a node at the top of the layer. So let's call that the top node. And then there are all the nodes below it. So let's call the nodes at the bottom of the layer the bottom nodes. The top node is some function of the bottom nodes. Well, we divided up the layers in such a way that now the top node doesn't depend on too many bottom nodes, because if k is large enough, then the top node is going to depend on smaller than log n bottom nodes. So there are going to be at most 2 to the c log n over k bottom nodes, which is at most n to the c over k. And as k gets larger and larger, this is going to be n to the epsilon. And of course, any function, Boolean function, can be written as a CNF or a DNF of exponential size. So the top node can be written as a CNF or a DNF of size at most n to the c over k times 2 to the n to the c over k as a function of the bottom nodes. And you can do this for each node in, you can do this for each layer, for the top nodes and the bottom nodes in each layer. And then you just put all these things together. So notice that this layer, which originally had depth c log n over k, now is going to have depth just 2. And they're going to be k layers, so the natural way of doing this will give you depth that's 2 times k. But we can do better by alternating CNFs and DNFs and then merging adjacent layers of ANDs and OR gates. So you'll just get depth k plus 1 rather than depth 2k. So you have this flattened layer. So each layer is now flat in the sense that it's a CNF or a DNF, something of depth 2, but of much bigger size. So this is where the size blow up occurs. So it's of size n to the c over k times 2 to the n to the c over k. And now you just compose all these circuits. And what you also do is that if you have 2 adjacent levels of AND and OR gates in this new circuit, then you merge them. So essentially, you'll just get 1 extra level for each layer. And so if you have k layers, then you're going to get depth k plus 1. And the size is going to be at most 2 to the n to the order 1 over k, because, well, there were at most that many nodes, and there were only polynomially many nodes in the circuit originally. And for each one, well, you have now maybe 2 to the n to the c over k new nodes, but the total size is still going to be 2 to the n to the 1 over k, order 1 over k. So this is a very, it's quite a simple divide and conquer approach, and it's, well, the important thing is that it's quite syntactic, so there's something that we can hope to carry over to the proof complexity setting and get the simulation there as well. But if you have any questions about this, yeah, just let me know now. Yeah.
This would seem to work also for branching programs, right?
Yeah, it's true. It's true.
Arbitrary width.
Yeah, so log space is in also
space can be done this way.
sub-exponential. Yeah.
So your thing would carry over a bit higher than Frege, probably.
Yeah, I mean, I'm not sure what the natural proof system there would be,
We
but
should ask Steve Cook about that. I mean, he has some proof systems.
okay, yeah, but it should probably. Yeah, that's right. Okay, so let's try to now, I'm going to try to sketch the proof of the main result. I mean, it gets slightly technical in places, but I'll at least try to convey the main ideas. So let's simplify the parameters now. So we're just going to start off with the polynomial in n size Frege proof, and we want to get a proof in constant depth Frege of size 2 to the n to the order 1 over k. So from polynomial go to sub-exponential. So let's say phi is a tautology with some proof, let's call it q of polynomial size, and let k be fixed from now on. So let k be some fixed depth that we want to simulate in. So how do we go about transforming this Frege proof q to k plus 2 depth Frege proof of sub-exponential size? Well, the natural idea motivated by this complexity theoretic simulation is just to replace each line of the proof by an equivalent sub-exponential size depth k plus 1 circuit, and the one that we obtained in this simulation. And let's see what happens then. I mean, do we still have a valid proof? So let in general, let's define this flattened form of a formula. So a a flattened form of a formula is just obtained by just carrying out the simulation that I described, just dividing up the formula into equal sized layers and simulating each layer by DNF or a CNF, depending on whether the layer is odd or even. So now you just take the proof Q and replace each line by f of psi. So certainly the size is going to be sub-exponential now because well, each line is going to have a sub-exponential size equivalent constant depth circuit. So the size of f of psi is going to be sub-exponential in psi. So the total number of the total size is going to be sub-exponential. And the rules of inference are still valid. So if you had a rule of inference in PK that you applied earlier, then when you make the substitution, it's still going to be valid. But of course, this is not going to be a valid proof, though, because, well, for more than one reason. So suppose we use a logical rule, and let's say we're using this AND introduction rule on the left. So we're deriving the formula. So the original rule is to get A and B and gamma yield delta from A, comma B, comma gamma yield delta. But now we're replacing all formulas. Well, I guess I should have also replaced gamma and delta by the flattened forms, but so that's a mistake. But so you're replacing now all formulas in the proof by the flattened forms. So what we're going to derive is f of A and f of B gamma yields delta from f of A, comma f of B, comma gamma yields delta. But this isn't really the flattened form of A and B. I mean, it's not true that f of A and f of B is a flattened form of f of A and B. So we have an issue here already. I mean, in fact, if you want this property of flattening to be preserved under ands and ors and negations, then well, the only possible f that does it is the identity. So you're not going to really gain anything this way. So you certainly don't have equality here. So that's one issue. We need to argue somehow that that these are equivalent, even if they're not equal as flattened forms. And also, what you're deriving finally is not phi, but f of phi. We've replaced each formula by its flattened form. So what you're deriving is f of phi. And then in order to get phi, we'll also have to argue that phi and f of phi are equivalent. And we need to argue this in constant depth Frege. So an idea for repairing it is, well, if we could show efficiently in constant depth Frege that for any A and B that well, f of A and f of B, or at least for A's and B's that arise in the proof, that f of A and f of B is equivalent to f of A and B, then we'd be getting somewhere. At least that first issue wouldn't arise. And in general, if you could show efficiently in constant depth Frege that the flattened form is equivalent to the original formula, then the second issue wouldn't arise. And in fact, if you show this, not just for and, but also for or and not, then you can use structural induction to show this for any formula phi in the proof. Because, well, any formula is either negation of something or the and of two formulas or the or of two formulas, and then you can just use structural induction together with the results of this form, the equivalences of this form, to conclude this. So, so all we need to do is we need to show that the flattened forms are equivalent when you apply these connectives, when you apply the and, or the or the not connective. So now so earlier we had a simple simulation where we just divided up the levels of the formula into fixed size layers. So the layers were all equal in size. But now this gets slightly more involved. So well, just slightly. So we want to prove the equivalence of f of A and B and f of A and f of B. So that's what we've reduced the problem to. So we have these flattened forms, and we want to show that the flattened form of A and B is equivalent to the flattened form of A and the flattened form of B. Where these flattened forms now all have depths approximately k and size is sub-exponential. And to do this, we are going to parameterize the notion of flattening. So we're going to extend it, and we're not just going to do the flattening using equal-sized layers, but it's going to be slightly more non-uniform. So we're going to do this parameterization using something called a depth vector. So there's just a sequence of depths at which you're going to cut the original formula, and then you're going to do the flattening as before. But now these depths are not going to be uniformly distributed. They can be arbitrary. So a sequence of integers d1, d2 to dk, where each di is bigger than di minus 1, that describes a depth vector. And the extent of the vector is just the maximum difference between depths, between successive depths. So it's a maximum over I of di plus 1 minus di. So somehow, if the extent is small, then the flattening is going to give proofs that are of not too large size. So the extent is what controls the size of the flattened form as a function of the depth vector. So now let's choose somehow for each formula canonical CNFs and DNFs corresponding to the formula. So this we can do easily. Let's say that C of phi together with V is the flattened form obtained by cutting the formula at levels D1, D2 to Dk, and then replacing the odd layers by canonical CNFs. So the first layer, the third layer, and so on by canonical CNFs, and the even layers by canonical DNFs, and then merging these layers. So now you're going to get a formula of that's k plus 1. And dually we define D of phi V. So now the odd layers are canonical DNFs and the even layers are canonical CNFs. So some of this duality comes in just because, just the way of dealing with negation in the proof. So one thing we can do, again by structural induction, is to prove efficiently in constant depth Frege that for any V that the conjunctive flattened form is equivalent to the disjunctive flattened form. So I'm not going to discuss how to do this, but this is something that can be done. And just a diagram which is perhaps not very illustrative of how you're doing this parameterized flattening. So earlier, all these, so you have these different layers, and earlier the size of each layer was the same, but now the layers are going to be controlled by these parameters, the di's. So d1 is just the index of this layer. So this is the d1th layer, and this is the dkth layer. I mean, so this is the dkth layer, and so d1 to dk is just an increasing sequence of depths at which you're cutting the formula. And then within each layer, you're doing the same thing as before. You're replacing each top node as a CNF or a DNF in the bottom nodes, and you're composing the resulting circuits. Okay, so the key lemma somehow is that this kind of invariance under parameterization. So it doesn't matter what the parameterization is. You can show that the flattened forms are equivalent irrespective of what parameterization you choose. So if you have two different depth vectors, and all you need is that their extent is small, which means that you get sub-exponential size proofs as a result. Then there are efficient constant depth Frege proofs that the conjunctive flattened forms according to these depth vectors and the disjunctive flattened forms are all equivalent. So all these four are equivalent. And I can, well, just say something briefly about how this works. Well, the idea is that you have these two different depth vectors, v1 and v2, and what you do is you gradually change v1 to v2, trying to show equivalence with each change. So you replace the first entry of v1 by the first entry of v2, and then the second entry of v1 by the second entry of v2 until you have completely transformed v1 to v2. And then for each such change, you want to show that there's an equivalence. So that's what I call a hybrid argument here. So essentially what you're reducing to is to prove equivalence for the case that just one new level is introduced or one level is removed from the depth vector. This again is not trivial, but you can essentially do this by a truth table proof. I mean, truth table proof is just where you consider all possible truth assignments and then check that the formulas are equivalent. And this is a proof that takes size, well, 2 to the d if your formulae depend on d variables, which would seem to be too much, but actually the truth table proof will only be for formulae depending on few variables. So this will still be in sub-exponential size. So essentially you have a hybrid argument and then finally reduce to this truth table case. But I'm not going to say much more about that. So that's just showing that depth vectors, well, it doesn't matter which depth vector you use, but how do you actually take advantage of depth vectors? So recall that the goal was to show that these two things were equivalent in constant depth Frege, that the conjunction of the flattened forms is equal to the flattened form of the conjunction. That's somehow what we wanted to show. So now you have, let's say you have some depth vector d1 to dk, let that be v, and then let v prime be a different depth vector 1 d1 plus 1 to dk plus 1. And now the key thing is that if you look at what happens when you apply this flattening to a and b, so let's say you apply this disjunctive flattening to a and b, looking at it according to the depth vector v prime is you're going to get the same formula as taking the conjunction of the flattened conjunctive forms of a and b. So essentially, well, maybe I'll try to draw a picture. So you're going to have an and here, and then here you're going to have d1. So this is A and this is B, and each of them have been flattened according to this depth vector d1 to dk. Well, now if you're doing this and, now you have a new layer of height 1. So essentially where you're cutting now, you're cutting at 1, and then you're cutting at 1 plus d1, and then 1 plus d1 plus d2 and so on. Sorry, is 1 plus d2 and so on. So that's just what it's reflecting. I mean, so essentially taking a conjunction means that you're introducing a new layer of size 1. So that corresponds to this depth vector 1 d1 plus 1 to dk plus 1. So now using this lemma we had about the invariance of the parameterization, we can show that the disjunctive flattening with v prime is equivalent to conjunctive flattening with v prime. And this is the same as the conjunctive flattening with v by that lemma. So now we get that the conjunctive flattening of A and B is equivalent to the conjunctive flattening of A and the conjunctive flattening of V. So this achieves the goal that we set out to achieve for and essentially a dual proof works for OR, and a similar proof works for NOT as well. So now going back, let me just remind you why this is enough. So as we remarked here, by structural induction, it's going to be enough to show that the flattened forms are equivalent under all these operations. I mean, then these issues disappear, and now this idea of replacing each line of the proof by the flattened form is actually going to give you a valid proof. Okay, so let's go on to corollaries of the main result. So the best known Frege low bound for constant depth Frege, as I mentioned before, is something it's 2 to the n to the some function that's inverse exponential in k. And this somehow seems inherent in this method of applying random restrictions, at least for the pigeonhole principle. So it's not known whether there are low bounds of the form 2 to the n to the 1 over polynomial in k. I'll mention that later as a very interesting open question. So the low bound is for the pigeonhole principle, and the pigeonhole principle is known to be provable in Frege, Samba. So our main result applies, and we can actually get a sub-exponential size, a constant depth Frege simulation of this. So the low bound is 2 to the n to the 1 over phi to the k, and the upper bound is something like 2 to the n to the 1 over k, essentially. So there's still quite a gap between the low bound and the upper bound for CNF tautologies. But if you're willing to allow more complicated tautologies, then you actually get a tight result, at least for the tree-like case. So Krajicek shows a low bound of 2 to the n to the omega 1 over k, so a better low bound in tree-like AC0 Frege. So this is for a sequence of tautologies, which is essentially the pigeonhole principle, except that each variable is now a so-called Sipser function of depth d. So these are functions that are hard for depth for depth k minus 1, and you can use that to get a stronger low bound. But note now that the depth of the tautologies is going to be larger than k. So the sequence of tautologies here has depth k plus 2, and you're trying to prove that in depth k Frege. So this kind of definition we had, where we're looking only at the depth of the cuts, is important because you can't insist that the depth of all lines is small. But our simulation still applied to this case. So so this sequence of tautologies also has polynomial size proofs in Frege, again using the result for the pigeonhole principle. And so we can apply our simulation to that case, and we get an upper bound of 2 to the n to the order 1 over k for sorry, I should have said an AC0 k, so a depth k Frege upper bound. So this is a low bound for AC0 k Frege, and the upper bound is also for AC0 k Frege. It's of 2 to the n to the order 1 over k and 2 to the n to the omega 1 over k. So now it's more or less tight in the exponent. But yeah, it's not clear how to do this to get a tight result for general DAG-like proofs or for CNF tautologies. So another interesting application area, in fact a motivating question, is this question of automatizability. So far talking about proof complexity, we've only spoken about the size of proofs, how large are proofs for certain tautologies. But very interesting question is also to find these proofs efficiently. So I mean, of course, we have a SAT solver, then the SAT solver needs to figure out a way of actually finding the proof, not just of verifying it. So how do we go about finding proofs? So this notion of automatizability of proof systems tries to capture efficiency of proof search. So we're going to deal with this notion of weak automatizability, which just says that there's some proof finding procedure which runs in time polynomial in the size of the smallest proof. So suppose you're given a formula phi as input, then the proof finding procedure is going to give you a proof in time that's polynomial in the size of the smallest proof for phi. So the size of the proof it gives you might be will be polynomial at most in the size of the smallest proof. Well, the one subtlety is that this might not be a proof actually in S, but it could be a proof in a different proof system. So somehow if you're doing proof search, you don't care as long as you get a proof for some correct proof system. So So we allow this, and that's why we have this term weakly automatizable. Strongly automatizable would mean that you actually get proofs in S itself. So that's a distinction here. And well, there's evidence. So it's kind of a frustrating situation because there's some proof systems for which you have strong low bounds. So the tautologies that don't have small proofs there. But for more powerful proof systems, tautologies might have small proof size, but finding the proofs is hard. So somehow either way you lose. And it's known for Frege that under some believable crypto assumptions that Frege is not weakly automatizable. And it's also known under a stronger crypto assumption about sub-exponential hardness that constant depth Frege is not weakly automatizable. And what we can do from our result is somehow derive the second result from the first result in a simpler way and a more generic way. So maybe I'll just say a little bit about this result, how it works. So I mentioned before this notion of feasible interpolation. So what that does is that for proofs of certain tautologies, it associates with such proofs a predicate which is efficiently computable. So if you have a small proof of the tautology, then you get efficient computability, like polynomial size computability for some related Boolean function. And if this related Boolean function is something coming from crypto, which is known to be hard to do, like the Diffie-Hellman problem, and if the original tautology somehow encode something with the Diffie-Hellman problem, which is a tautology, and provable efficiently in Frege, then having polynomial size proofs in Frege would imply that Diffie-Hellman is easy. So under the assumption that Diffie-Hellman is hard, you get that Frege doesn't have this feasible interpolation property. And that actually implies that Frege is not weakly automatizable. There's a connection between feasible interpolation and weak automatizability. And it kind of translates. So how does the result yield this from this? Well, if you had polynomial size proofs in Frege of these Diffie-Hellman tautologies, and that gives you sub-exponential size proofs in constant depth Frege. So if you can weakly automatize constant depth Frege, then in sub-exponential time you can essentially solve the Diffie-Hellman problem. So under an interactivity assumption about the Diffie-Hellman problem, which is stronger, sorry, that it has a purely exponential hardness, you actually get that constant depth Frege is not weakly automatizable. But now this is done in a more generic way than was done in the earlier paper, where it was specialized to Diffie-Hellman problem. Now essentially any sequence of tautologies in Frege which give you this non-automatizability can be translated to give you non-automatizability of constant depth Frege. So there's somehow more room to play with. And an interesting related question here is automatizability for very low depth Frege. So resolution is like depth 1, and it's not known if resolution is weakly automatizable. There's a big open question. It's known that it's unlikely to be strongly automatizable, whereas nothing is known of weak automatizability. And our result could potentially be used to give evidence against automatizability for really small depth Frege. I mean, maybe k as small as 5, but probably not smaller. So there's still a gray area. So like k being 2, 3, or 4, it's not clear whether it's automatizable or not, or what the evidence is. So there is certainly, based on this, again, proof based on game theory, there's some evidence. So I guess that's for DNF resolution also. For depth 2.
So depth 2 is not weakly automatizable unless mean of games can be solved in polynomial time.
Right, yeah. And that's
simple stochastic games.
But that's very likely.
Well, it's not likely. I would say it's at least 30 years of problem now.
So what is
30-year-old problem to solve mean pay of games in polynomial time?
Still doesn't mean it's not likely.
At least there is a connection between the two.
So what should be like whether the conjecture is true or that there is around it?
These games can be solved in polynomial time.
well, I think some people believe they can be solved in polynomial time. Some others don't. So it's kind of a Okay, so what are the main open questions? Well, maybe my favorite one is trying to get a tight result. So we got an upper bound, but to get a tight lower bound for CNF tautologies and depth k Frege. So to actually find a sequence of tautologies for which you require proofs of size 2 to the n to the omega 1 over k in depth k Frege.
Do you have some candidates?
No, I haven't really thought about it. Do you? Is that? You're not going to say it. The pigeonhole principle, it could be a candidate, but I don't know, the proof technique somehow, the random restriction technique doesn't seem to.
Well, you need better switching limit to do it by the same method, right? But
So I wonder whether there is actually a formulation of like a better switching lemma which would give you automatically a better result. I mean, I'm not sure.
Well,
whether
if you look at the Hastad switching lemma in the Boolean case, then you have a good enough switching lemma because he gets lower bounds of depth log n over log n for polynomial size circuits for parity.
Right.
But here, it's not quite as good a switching lemma for the pigeonhole.
But
setting.
it's also something to do with the nature of the pigeonhole principle. I mean, that's the reason why a switching lemma isn't very good, because you need to somehow restrict both sides, and I mean that gives you a loss. So you somehow go to square root n with each depth rather than just n over some constant. Yeah, but it's an it's an interesting question. Just PHP might be a good candidate, but I don't know about how you go about showing it. A different candidate with random restrictions used more normally could also work. It's people have tried. I mean, it's been attacked quite a few times. Okay, so well, Albert pointed out that something else interesting is known about automaticity of depth 2 and depth 3, but we'd like more interesting things to be known about this. And well, another direction is to take advantage of complex simulations in other settings. So one paper that recent paper that I find quite interesting is a paper of Hrubesch and Yehudayev, where there's this was open problem of proving the determinant identities, it was open whether this could be done in Frege, and they settled that problem by using somehow techniques from arithmetic complexity. So they have this notion of an arithmetic proof system, and then they translate different complexity simulations in arithmetic complexity to results in this proof system, and thereby they settle this question, which is again a question that is open for a while. And there are other interesting simulations in arithmetic complexity. For example, in arithmetic complexity, essentially depth 4 is equivalent to the entire case. So general arithmetic circuits, exponential lower bounds for them are equivalent to exponential lower bounds for depth 4. And maybe there's also a proof complexity version of this, which would also be interesting. Okay, so that's about all I have to say. Thanks.
So there has been already some discussion, but we can continue. We still have a couple of minutes time. Yes.
So in the middle of the talk, you mentioned something about log space, which is a superclass of the NC.
No, Albert mentioned something about it. Yeah.
What did you mean? This whole thing somehow applies?
No, it was Albert's observation. So that log space, the complexity simulation works for log space. Log space is also in sub-exponential constant depth circuits. So you could imagine getting a proof complexity. If there's some kind of proof complexity analog of log space, then you could try to simulate that with constant depth Frege. That'd be a stronger result.
I see.
Where the lines correspond to branching programs. Yeah.
Moshe?
So there's been in the last couple of years a major progress in circuit complexity. Is there any chance of this trickling down to proof complexity?
Well, I mean, there's one specific case where there is some chance, I think. I mean, it's something we thought about. So it's a result that for some natural problems like a Boolean formula evaluation, you're just given a formula and you want to evaluate it. Now, if this has threshold circuits of size n to the polynomial size, then it also has threshold circuits of size n to the 1 plus epsilon for any epsilon greater than 0. So it's somehow a result where you get just given polynomial size formulas of circuits, you get much smaller ones. And you can think about trying to prove a proof complexity analog of that. But it's more difficult because somehow you're trying to compress the proof rather than expand it. So you can't use a black box approach, which is just replacing each line of proof by something. I mean, you somehow need to argue in a more clever way. So that's a complex simulation that's more challenging, I think, to translate to a proof theoretic setting. But but maybe you were referring more to the Williams results. But the Williams results, I mean, there I don't really think, because they're just combination of like different structural complexity techniques like diagonalization and like algorithmic ideas. So it's quite important that the complexity result is kind of syntactic, because so that we can argue about it with low complexity proofs, while it's probably not the case for the Williams result. Yeah.
Just remarks on this log space question. So let me point out that Sebastian Miller has a paper where he proves this simulation by kind of a high-level argument via bounded arithmetic, while formalizing Nepomniachtchi's theorem there.
Right.
And therefore it follows that for any proof system where the lines can be evaluated in polynomial time and sublinear space, the same type of argument applies.
Yeah.
Now it's much easier to formalize this in bounded arithmetic because you don't have to worry about the syntax of proof system, just that the theory corresponding to this class proves soundness of the proof system, and then automatically the simulation applies.
Yeah, so let me actually say, I mean, yeah, in general it gives that polynomial time and sublinear space is in sub-exponential size AC0. Yeah.
Yes.
If there's time, another comment. So you know, in proof complexity, unlike in circuit complexity, the monotone sequent calculus and the non-monotone one are close together. There is a quasi-polynomial simulation.
Okay.
And then I noticed that your flattening preserves monotonicity of the formula.
You're right.
So the question is then, what happens with the simulation of the other part? Does it preserve monotonicity? In which case, if it did, you would get your problem translating back to monotone bounded depth.
Yeah, I mean that should be the case, I would think.
You think the simulation preserves monotonicity?
Yeah, I mean, I guess I need to think about it a little more. But if it did, what kind of consequence would it derive?
Well, then it would suffice to have lower bounds for monotone bounded depth.
Oh, so it's an explanation for why those lower bounds are hard to obtain.
Yeah, depending on how you read it.
Yeah, so we should talk about that. Yeah, thanks.
Okay, more questions? If not, then thank the speaker again.